Okay, welcome my friends. Here we go. We're going to start the review for physics end of level test. We got our class final coming up, and also the state exam is coming up. So I know it's been a long time since we've talked about some of the stuff we learned in first quarter. So that's going to be the purpose of this video, is to review some of the topics of first quarter physics. So what we've done was we've made a little booklet like this in class. We folded it. It's got 8 pages. So the first cover is number 1, the front cover is number 1, and the back cover is number 8. So we're going to go through it slowly, and each page is going to review a concept that's so important for you to know. And I hope that it works for you. I hope that it's a good review and that you can use these little booklets as you go through the review process for the next 2 weeks. So let's get started. So what I've got is this first page. Looks like this. Okay, so on the front cover, you're just titling this front cover number 1. We're titling it Physics First Quarter Review. And then I just drew a little picture. It's supposed to be a Newton's cradle. Some physics picture if you like. Keep it small. Remember, all of this has got to fit on that small front cover of yours. So you need to scale it appropriately so that you have enough room. Real quickly, we reviewed in first quarter the difference between a scalar and a vector. A scalar is a quantity that it's a magnitude only. Which I put in parentheses here that it's a number. It's just a number only. For example, 65 miles per hour is a scalar quantity because it's just a number. Now let's contrast that to what a vector is. Vector is a magnitude and direction. So it's a quantity that shows magnitude, which is a number, and also the direction. So here's an example of a vector. 65 miles per hour north. And we talked about how vectors, we could draw them as arrows. The length represents the magnitude, and of course the direction that it's pointing shows us direction. And so hopefully that kind of brings back into your mind what we talked about in the very first day of physics. The difference between a scalar and a vector. So please hit pause in your video right now until you've got all of this copied down onto your front cover. Once you do, then hit play and we'll go to page number 2. Okay guys, let's go to page number 2. Again, all of this needs to fit on page number 2. So you need to scale your writing accordingly. We're going to title it Distance versus Displacement. We want to know the difference between distance and displacement. And so what I've done is I just wrote the definitions for distance and displacement, and then I've given you an example problem. So distance is the total distance traveled for the entire trip, including the curves. It's the total distance. You have to add it all up. Well, displacement is the difference between final and initial position. So it's how far away you are from your initial starting point. So this is a straight line distance between your initial starting point and your final starting point. So that's displacement. Much different. Okay, here's my example. I wanted you to draw a lap around the track. So this is 1 lap is 400 meters. And draw a little stick figure for you. Well, one time around the track, if you ran one time around the track, your distance, the total distance, is 400 meters. But your displacement, what is your displacement going to be? 0, because you came back to the same exact spot. You don't have any, there's no difference from your initial position and your final position. So your displacement will be 0 meters. And hopefully that kind of helps you remember the difference between distance and displacement. I'm going to hit pause. If you're not done writing, please hit pause until you're finished with page number 2, and then we'll go on to page number 3. All right, let's go on to page 3. Page 3, I'd like you to title it Speed versus velocity. Speed versus velocity. In this page, we want to kind of learn the difference between speed and velocity. They're very different. So again, all of this needs to fit on page number 3, so you need to scale your writing accordingly. So speed is equal to distance divided by time. And distance is measured in meters and time is measured in seconds, so the units for speed is meters per second. Now let's contrast that to velocity. Velocity is equal to displacement over time. Displacement is measured in meters and time is measured in seconds, so the units for velocity are meters per second. We need to remember that. Okay, so speed and velocity are very different because speed is distance over time and velocity is displacement over time. I've got an example problem that kind of illustrates this. So I'd like you to include this example problem on this page. Just draw a track. Again, one lap is 400 meters around the track. And let's say you run one time around the track in 2 minutes. Well, let's change that to seconds. In 2 minutes, how many seconds are there? 120 seconds. Now, let's calculate the speed. Speed is equal to distance, so the distance that you would have to run around the track is 400 meters. The time that it took you is 120 seconds. So if you take 400 and divide it by 120 in your calculator, you get 3.33. Again, the units are meters per second. So your speed is 3.33 meters per second. Now let's contrast that to velocity. Velocity is equal to displacement over time. So because you came back to your starting position, you have 0 displacement. Divided by the time, you still took you 120 seconds, but 0 divided by 120 is 0. So your velocity is 0 meters per second. Much different. Speed and velocity are very different, and hopefully that kind of helps illustrate that. All right, that's it for page 3. So take your time and write that down. If you're not quite done writing, hit pause on your video, and when you're ready, hit play, and we'll go to page 4. All right, that's it for page 3. Let's go to page 4. I want you to title page 4 Average Velocity. So title it Average Velocity. I've got a definition. So again, all of this needs to fit on this page, so you need to kind of plan accordingly. The definition for average velocity is change in displacement divided by change in time. This little triangle here, we spent a lot of time talking about it in first quarter. This triangle is a Greek letter. It's delta. But whenever you see it in physics, it means change. How you calculate change is you take the final minus the initial. So anytime you see this little triangle, it's final minus initial. I hope that you guys will remember that. Please make note of that on this page. I've got an example problem for calculating average velocity. But for my example problem, I need you to make this table here. It's got 2 columns and 1, 2, 3, 4, 5, 6, 7 rows. So make that column, or make that table. In the first column, I want you to put time in seconds. And it goes from 0 seconds, 1, 2, 3, 4, 5 seconds. For the position column, title it position. We're measuring position in meters. And we're starting at 0 meters. We go to 2, 4, 6, 8, and finally 10 meters will be our final position. All right, so after you make that table, I've got a question. Here's my example question. I say, what is the car's average velocity from 0 to 5 seconds? So if we want to calculate its average velocity from 0 to 5 seconds. Here's how you will do that. I hope that you will write down average velocity equals change in displacement divided by change in time. And again, change means final minus initial. So we're talking about final or change in displacement. We're doing final displacement, which is 10 right here. So 10 minus the initial displacement, which we get right here, was 0. So 10 minus 0 goes on top. The change in time goes on bottom, so the final time period that we had was 5 seconds. So that's first, minus the initial time was 0. And so when you simplify this, you get 10 on top divided by 5. 10 divided by 5 is equal to 2. And our units for velocity are meters per second. So that's the average velocity for this entire trip from 0 to 5 seconds is 2 meters per second. And that's how you will find average velocity. Hopefully that will help you. That's it for this slide. So again, hit pause until you've got it all written down on page number 4. Once you're done, hit play and we'll go on to page number 5. Okay, so that's average velocity. Now we're going to go to page number 5, and it's going to be similar to this, but we're going to do average acceleration. So on page number 5, I want you to title it Average Acceleration. And again, it's all got to fit on page 5, so scale your writing accordingly. Here's the definition for average acceleration. Here's how we find it. It's equal to the change in velocity divided by change in time. The units for acceleration, I hope that you will remember this, are meters per second squared. Anytime we have acceleration, it's meters per second squared. To help us remember, I've got an example problem. And again, for our example problem, we need a table. Again, this is a 2-column table with 1, 2, 3, 4, 5, 6, 7 rows. For the left column, I want you to title it time in seconds. So we're starting at 0 seconds and going 1, 2, 3, 4, and finishing at 5 seconds. The second column, I want you to title it velocity and put meters per second in parentheses because that's the units. We're starting at a velocity of 0, then going to 2, 6, 10, 12, and final velocity at 5 seconds will be 15 meters per second. So once you've got that table made, then I've got an example problem in calculating average acceleration. So I have a question here. It says, what is the car's average acceleration from 0 to 5 seconds? So I want you to write down at the bottom, average acceleration is equal to delta v over delta t. Change in velocity over change in time. So again, the delta sign means change. We're starting with final. Our final velocity was 15, so that's where we're getting the 15 right here comes from our final velocity. Minus the initial velocity at 0 seconds was 0, so that's where we're getting that 0 right there. That's on top, that's our change in velocity. Divided by change in time, again, it's final minus initial, so final time was 5 seconds, minus the initial time of 0 seconds. And when you simplify this, 15 divided by 5 is equal to 3. And it's 3 meters per second squared. The units for acceleration will always be meters per second squared. So that is his average acceleration throughout that 5-second time interval. He averaged an acceleration of 3 meters per second squared. All right, that's it for page number 5. So if you're not finished with the writing, please hit pause. When you're done, hit play, and we'll go to page 6. Okay, so that's it for page number 5. Let's go to page 6 and start reviewing some of the motion graphs that we learned in first quarter. Now this, guys, was some of the hardest or more difficult concepts for students to learn about. So let's review, first of all, position versus time graphs. So on page number 6, title it Position versus Time Graphs. And all of this has got to fit on page 6, so you're going to have to write pretty small. But first of all, in this box right here, this is so important to remember when you're trying to logic through and think through position time graphs. For position time graphs, the slope tells you velocity. So the slope of the line tells you the object's velocity. Curved lines, if it's curved, tells you that it's accelerating. So slope tells you velocity, curved lines tell us acceleration. Now what I've done is I've put 7 examples. These are all the examples I could think of for position time graphs. So let's go through them. The first example is right here. I want you to make a little position time graph and draw the line in. For number 1, it's just a horizontal line. Well, if you look at this, it has no slope. So if it has no slope, it has no velocity. Velocity is 0. This object has to be at rest. It's not moving. It's just staying in the same position. Let's go to the second example. This position time graph now has a slope. It has a positive slope. It's going up. Because it has a positive slope, that tells us that it has a positive velocity. So it must be moving to the right. In physics, to the right or up means positive. So I put constant velocity to the right on number 2. How do we know it's constant velocity? Well, there's no curve. It's a straight line. So velocity is staying constant. Let's go to number 3. For this position time graph, we see a line that goes down and to the right. So it has a negative slope. That negative slope, again, slope tells us velocity, so it has a negative velocity, and negative in physics means it's going to the left, or it could be going down. So this is going to the left at constant velocity. Again, constant because it is a straight line. There's no curve. Okay, number 4. For this position time graph, now we see this curved line going up and to the right. So if we see a curved line, I'm hoping that you recognize that there is acceleration happening here. Now the slope at the very beginning is almost horizontal, so that means the velocity is slow right here. But as time goes on, the slope becomes more severe, which means its velocity is increasing. So if the velocity is getting faster and faster and faster, that's the definition of acceleration. So this thing is accelerating, and it's going to the right because the overall slope is positive. So this is acceleration to the right. Let's go to number 5, in this position time graph. We notice that it's curved. First of all, you should notice that it's curved. So there's acceleration going on here. But it's curved going down, so the velocity, because the slope is negative, the velocity is negative, which means it's going to the left. But now I want to go through, at the very beginning, the slope is almost horizontal, so that tells us that this has a velocity of almost 0 right here. But as time goes on, the slope becomes more severe, so it's speeding up. So it's going slow right here and then speeding up as time goes on. So this is accelerating to the left. Now let's go through the final 2 examples. Number 6, first of all, you notice it's curved. So there's acceleration going on here, or deceleration. At the beginning, the slope is pretty severe. As time goes on, at the end, there's almost no slope. So that tells you that the velocity is getting closer to 0. So it's slowing down. Deceleration, and it's going to the right because the overall slope is positive. So it's got to be going to the right. Number 7. Again, it's curved, so we see it, you should notice acceleration right off the bat. It's fast at the beginning because the slope is more severe, but as time goes on, the slope goes to 0, so the velocity goes to 0, which means it's decelerating. How do we know it's going to the left? Because the overall slope is negative. Okay, I know those can be a little bit complicated for students, and hopefully that helps you remember position time graphs. So if you're not done writing all of them in, hit pause on your video at this point. Once you've got them, then hit play, and we'll go to page number 7. All right, guys, let's go to page 7. Page 7, I'd like you to title it Velocity versus Time Graphs. So velocity versus time graphs. Again, all of this has got to fit, so make sure you're writing kind of small. The first thing that I want you to know about velocity time graphs, or to think about when you're going through these problems, is what's in this box right here. This is the most important to remember. For velocity time graphs, the slope now is going to tell us acceleration. Curved lines, you're not going to see any curved lines with my examples. So I'll never have curved lines with my velocity time graphs. Also, the area under the curve of a velocity time graph tells us the object's displacement. So that's kind of cool that you can figure that out from a velocity time graph. What I've got is, again, 7 examples. All the examples I could think of. So let's go through them, and hopefully this brings back into your memory how to think about velocity time graphs and know what the motion of the object is. So in this first example, a velocity time graph is drawn a little bit different. We have a positive velocity upstairs and a negative velocity downstairs. And right at this 0, this is velocity of 0, and that's this first example, the velocity is 0. So if you see a velocity time graph like number 1, the object is at rest. It's not moving. Velocity is 0. So it's at rest. Number 2, you'll notice with this velocity time graph that the line is drawn upstairs, which means it has a positive velocity. But this line right here has no slope. If the slope is 0, it's not accelerating. So it has positive velocity with no acceleration. That means constant velocity to the right. It is still moving because it has velocity. So it's just constant velocity to the right. Now, what if you see that horizontal line downstairs, like on example number 3, the velocity is negative, but it's a line with no slope, so it's not accelerating. So it's constant velocity, but now the velocity is negative, so it's to the left. Left in physics is negative. Okay, let's go to 4. If you see a velocity time graph like this, we'll notice that the line is upstairs, which means it has a positive velocity, so it's going right. But now the line has a slope. Slope tells us acceleration, and so this is a positive acceleration to the right, or accelerating to the right. Notice, guys, the line is getting further away from 0. It's getting faster and faster. It's speeding up, and it's going to the right. Let's go to number 5. On this velocity time graph, now we notice the line is downstairs where it has a negative velocity, so we know it's going left right off the bat. We know it's going left because it's got a negative velocity. It's downstairs. But now we need to look at the slope of this line. It has a negative slope, so it does have slope, so it is accelerating. So if you'll notice, guys, it's starting at velocity of 0, and it's getting further away from 0. So this is speeding up or accelerating to the left. 2 more examples. Number 6, if you see a velocity time graph like this, now the line is upstairs, which means our velocity is positive. So we're going to the right. Positive velocity in physics, that's to the right. But you'll notice that it does have a slope, but slope is negative. And notice, the velocity is fast at the first, but the velocity is getting closer to 0, which means it's slowing down. So that's deceleration. So it's decelerating to the right. Number 7. You'll notice that it's downstairs. Our velocity is negative. So right off the bat, you should say, well, it's going to the left, but let's figure out what its motion is to the left. It has a positive slope, and slope tells us acceleration. And so if it has a positive acceleration, let's look at this, though. It's going to the left, but is it speeding up or slowing down? I want you to think about that. Is it speeding up or slowing down? If it's getting closer to 0, it's slowing down. So this is decelerating to the left. It's decelerating because it's getting closer to 0. I hope that you can logic through some of these velocity time graphs with that. So that's it for page number 7. Again, if you're still writing, hit pause in your video. Once you're done, hit play, and we'll go to the final page, page 8. All right, let's go to the final page, page 8. And this should be your back cover. And let's keep it pretty simple. Let's finish off with an easier topic. This was motion dot diagrams. We also called them ticker tape diagrams. And so title page 8, motion dot diagrams. And I've got, let's see, 4 examples here. So write examples, and we're going to do one at rest, one at constant velocity, one where there's acceleration, and one where there is deceleration. So if you remember these dot diagrams, you got to kind of think of it as a car that's losing oil. So there's an oil drip. But the oil drip happens at consistent intervals every time. And so if you'll notice, if you are at rest, or the object is at rest, this car is at rest, you're just going to see a bunch of dots right on top of each other. It's not moving. There's no distance between the dots, which means that the car or the object is not moving. It's at rest. Now, what if your car was going at a constant velocity, so you had it on cruise control? Well, you will notice that the oil drops here are a consistent distance apart. So these intervals are the same. At least they should be the same intervals. Okay, now with acceleration, what you're going to see with motion dot diagrams is that they're going to start close together, but if it's accelerating, it's covering greater distance every second. And so the distance between these dots increases every time. And so we started really close together, and then we finish way far apart. All right, and then finally, let's show deceleration. So deceleration is when we're going fast and then we slow down. So if you're going fast, there's a greater distance between the oil drops. So the greater distance between the dots here. Now as we slow down, the dots get closer together until if you came to rest, they would just be on top of each other at the end. And guys, that's first quarter. That's all the stuff we learned in first quarter. I hope that this making this little booklet will help you review, and you can use it as we go throughout the next 2 weeks reviewing for our physics exams. And that's it. So we'll finish there.